So let's solve some simple problems now. So imagine we have a 6 byte long, right? The length is 6 bytes, PC relative jump instruction, right? So the jump instruction itself is 6 bytes long. The instruction is 6 bytes long, right? And the addressing mode used here is the PC relative addressing mode, and it's a jump instruction. This is stored at address 543025 in decimal. Okay, so this is the starting onwards. So which means in address 543025, right? So in this address location, right? Let's assume this is my memory. In this address location, this instruction is stored from this address onwards, right? So, and it's a 6 byte. So if this is 1 byte, so this is my first byte, my second byte, so this is in decimal, right? So 26, 27, 28, 29, right? So 1, 2, 3, 4, 5, 30. So this whole instruction requires 6 bytes, right? So the whole instruction, the jump instruction with PC relative addressing is stored in these 6 bytes, right? So the next instruction will be at 543031. This is where you will have your next instruction. Okay, let's remember that. So this whole thing is occupied because this instruction requires 6 bytes. Okay, cool. Now what it says here is minus 48. This is the signed displacement value present in the address field. So how does the jump instruction look like? You will have jump and you will have the relative address. This relative address is also sometimes referred to as the displacement. And this relative address field has a number minus 48. It's a signed integer. Here your relative address value is minus 48 that is stored in the address field, right? In this relative address field. Now there are multiple questions here. Let's go one by one. What is the branch address? Which means where do we branch to, right? So imagine if I have this jump instruction. So let's see, what will my program counter point to? Look at this, while this instruction is being executed, this instruction requires 6 bytes, right? What will my program counter point to? My program counter will point to 543031, right? So what is the branch address or what is the effective address that we will branch to? That's the question here. So whatever value is there in the program counter, we add the relative address. The relative address is minus 48. This is the effective address that we will branch to, right? So if I add this, what do I get? I get 542983. So this, again, all these numbers are in decimal, thereby making the math simple for us, right? So this is the effective address, or this is the branch address that we will branch to after executing this unconditional jump. Again, here the important part here to remember here is that the instruction itself is 6 bytes long. So where will your program counter point to? You need to compute that. Then the minus 48 is there in the relative address or in the displacement field. Very simple question here, right? So now let's look at the second part. If the base register contains 683823, what is the branch address? What is the address that we will branch to if base register address is used? Okay, so if base register addressing mode, okay, so instead of PC relative addressing mode, if we use base register addressing mode, right, that's very important. If we use base register addressing mode, and if the base register, so the base register contains this value 683823, right? So what will my instruction look like? My instruction will have jump, the base register value. Suppose the base register is, let's say, R1. Okay, so let's say this is my register R1 and there is an offset, and that offset here is minus 48, or the displacement here is minus 48. So this displacement value here is minus 48. Now where will this jump to? Let's see. So what is the effective address that we will jump to, or what is the branch address that we will jump to finally? In this situation, whatever value you have in the base register, we add this minus 48 to this. Right, because this is the base register contains, look at this. If you look at the pictures, right, the base register will contain the first address of the segment, and the address field itself, or the displacement field, is the displacement within that segment. So if I perform this, what do I get? I will get, again, whatever result I get, this is the branch address. Very simple math. You can just use a calculator and compute this quickly. Okay, now there is a third type of addressing mode, which is a mixture of multiple things. So sometimes people also use based indexed addressing mode. Look at this, they're doing both based as well as indexed addressing mode. Again, here we have learned what is indexed addressing mode, right? Like the array indexed. Based basically means you have the base address. So what does it say? This addressing mode uses both the base register and an index register with the index value equals to 32. Then what is the branch address? Okay, so how does this work now? What is the base register address now? Base register address will take the same address, 683823 in the base register. What is my index value? My index value is 32. Then what is my displacement value, or what is my relative displacement or relative address or offset value? My offset value is 48. So this is the address of your branch address. Again, based indexed addressing mode is not something that is used extensively, and hence I did not cover it in the course videos. But this is a very simple concept, right? Based basically means you have a base register which will give you the segment base address. Index basically means you have an index register which will give you the index value, and you have the addressing mode, right? And this is used for your for jump instruction. The moment you know that it's used for jump instruction, you will have a displacement value. The displacement value given is minus 48. You simply add them and you get the branch address. Very simple concept here, right? So don't get confused if you come across a term which you have never encountered, because you can easily make sense out of it. You know what indexed is, you know what based is, and it's a jump instruction, which means there has to be a displacement or offset or relative address field. Very simple. Again, different books use different terminologies. Some books use this concept called displacement. Some books use the terminology called relative address. Some books use the term called offset. Don't worry about these terms. Once you get used to these terms, they'll all make logical sense to you, right? Very simple question. So let's go to the next question now. Let's look at this question. This question says that you have a 2-byte instruction. You have a 2-byte instruction that is present in the memory location starting at 254. Okay, so it's starting at 254. That's the memory location it is starting at. It's a 2-byte instruction, right? So in memory location 254, this instruction starts. This instruction is 2 bytes, so it's also there in byte 255. Okay, unless otherwise stated, we'll simply assume that this memory is byte addressable. So these two you have the instruction. The next instruction is starting from 266. Okay, then it also says that your instruction requires 2 bytes, right? The first byte is the opcode. The second byte is the address, right? The second byte here is the address field. And what is stored in the address field? The value 232 is stored in the address field. This address field has 232, right? And the memory location, in memory location 232, you have a value 185 stored. All these numbers are in base 10, right? You have a register R1 where value 222 is stored. Okay, these are 3 things that you have. And you have a jump instruction now. Let's assume we have a jump instruction. Now, what is the effective address if we use immediate addressing mode? Look at this. If we use immediate addressing mode, what again? You got the context, right? For different addressing modes, we'll see what is the effective address now. Very simple question. So you have a 2-byte instruction. The instruction is there in these 2 bytes. The first byte is the opcode. The second byte, the address field, what is called as the address field, contains a value 232. In memory location 232, you have value 185. In register R1, you have value 222. Right? Now let's go step by step, and for various things, let's compute this. What is the calculate the effective address? Calculate the effective address if you are using immediate address mode. If you are using, so let's assume I'm using immediate address mode. Again, this opcode could be jump, or this could be some move like operation. It need not be jump, right? Because we typically don't use immediate addressing mode for jump like instructions, right? So this opcode need not be jump. It could be anything. We want to compute the effective address, simply speaking, for any type of opcodes. Okay. So calculate effective address if we are using immediate addressing mode. So in immediate addressing mode, whatever value is here, that is used as the data. Whatever value. So 232 is used not as an address, but as the data to this opcode. Right? That's how immediate addressing mode works, right? Now what is the concept of effective address here? Where is this value 232 stored? This 232 is actually stored in the second byte here. Look at this. This 232, this is the first byte, right? This is stored in byte 254. This is, so let me write this down. This is stored in byte 255. So the effective address in this case is 255 because my data is 232. Because in immediate addressing mode, what do? Whatever is there in the address field, I use it as the data itself. Because I'm using it as the data, where is this data located? This data is located in address 255. So what is the effective address? 255. This is a small twist here. Okay, but it's a very simple concept. If you understood how immediate addressing mode works, effective address is very simple. Effective address is where is the data stored? Because we know this address field itself is data in immediate addressing mode, and this is stored in byte 255. My effective address is 255. Problem solved. Right? Now let's look at the next one. What if I'm using register address mode? And let's assume I have only one register here, just for simplicity. My register address mode with R1. Okay, so if I have register addressing mode, what does that mean? It means, so what will be my effective address here? In register addressing mode, we say that a data resides in a register. This address will now point, so this, whatever is the value of this address, whether it's 232 or whatever it is, because we have only one register, this will point to the single register. So in here, what is my effective address? My effective address is nothing but the address of, my effective address is the register address of register R1. Because we are only given one register and no other register. Okay. So what about direct addressing mode now? So what about direct addressing mode? In direct addressing mode, the address is looked at as an address of where the memory is located. Right? So in memory, so this value, this address field has a value 232, right? So this has value 232. This has the opcode, right? Let's see this here. So in direct addressing mode, this is used as the address of the data, which means your effective address here is 232 itself. Very simple, right? What if I have register indirect addressing mode? Look at this, register indirect addressing mode. In here I have only one register, which means whatever is there in the register, that is, so whatever is there in 222 is the data, which means my effective address here is 222 here, because that's where the final data resides, right? So imagine if I'm using memory indirect addressing mode. If I am using memory indirect addressing mode, how does that work? It works like pointers, right? So 232 is here. Where does 232 point to? If I go to memory location 232, I see 185. I see 185. In memory location 185 is my data. So my effective address in this case is 185. Remember, effective address is the final address where your data resides. That's very, very important to understand, right? Now let's look at indexed addressing mode. Imagine I'm using indexed addressing mode where R1 is the index register. Look at this, where R1 is the index register now. Now what happens? Now, so what is my, so in your index register, in your indexed addressing mode, what do you have? You have an index register. The index register value is 222, right? The index register value is 222, and this I will use it as my base address. Look at this. In index addressing mode, what do I need? I need a base address, right? And I need the starting address, which I'll use from the address, from this address one, and my index register itself is my R1. That's what it clearly says here. So I'll take 222 as my index. I'll use this as my base address. My base address here is 232. So if I sum up both of them, I get 454. So this is now my effective address. If I'm using indexed addressing mode. If I'm using PC relative addressing mode, then what happens? Look at this. If I'm using PC relative addressing mode, while this instruction is stored in these 2 bytes, where will my program counter point to? My program counter will point to this. So my program counter will have a value of 266. To this, I will interpret this as an offset. I'll interpret this as an offset. So to this, I will add plus 232. I will add plus 232, which will give me, 400. So let me erase this. So which will give me 498, right? 498. Yes. So this will give me 498, right? Sorry, this is not 266. This is 256. I'm sorry. This is 256. So if this is 256, sorry, my bad. So this is not 266. This is 256. My bad. Okay. So my program counter will have 256. So this will be 488. So the effective address now is 488. Again, for PC relative addressing mode, we are assuming that we have a jump like instruction. For rest everything, it is some address of the final data that we need for this opcode, for this instruction to be executed. Simple. Again, here in one simple example, we have touched upon multiple addressing modes. Again, always look at what you have in register, what is there in the address field, how we can interpret it. Okay, very nice example here. Now let's look at another example here, right? So imagine, consider a RISC machine. Again, don't worry about what RISC is. RISC is one of the architectures or one of the concepts behind how microprocessors work. We will discuss this when we learn about instruction sets in lots of detail. For this question, this is not important. So let's just ignore this. So consider a microprocessor where each instruction is exactly 4 bytes long. Okay. Conditional and unconditional branch instructions use PC relative addressing mode. Cool. With offset specified in bytes to the target location of the branch instruction. Offset specified in bytes, which means the memory is byte addressable. Cool. Now further, the offset is always with respect to address of the next instruction in the program sequence. That's what PC relative addressing mode is. They're just explaining what it is. Consider the following instruction sequence. I have instruction 1, instruction 0, 1, 2, 3. If the target of the branch instruction is I, look at this. I have some add instruction, some subtract instruction, some comparison instruction. This is branch if equal. Look at this. BEQ has to be read as branch if equal. Okay. This is like jump. This is like jump if these two are equal or something like that. Okay. We don't have to understand this. So what it says is here is if the target of the branch instruction is I, which means if this condition is true, we want to jump to this instruction I. Then the decimal value of the offset is, okay, let's see. So this occupies. So let's just take a simple example, right? So let's assume this starts from address 0. Okay, look at this. It says each address is 4 bytes long. So from 0 to 3, these 4 bytes will be occupied by this instruction. From 4 to 7, these 4 bytes will be occupied by this instruction. From 8 to 11 will be occupied by this instruction. From 12 to 15 will be occupied by this instruction. And while this instruction is getting executed, your program counter, look at this, your 16th address location, your program counter will have an address of 16, right? Now, what do you want? You want to branch from here back to here. This instruction is starting from address location 0. So if this condition is satisfied, you want to jump here. The question here is, what is the value of this offset field? That's the question here. So if your PC is 16, if this is equals to 2, which address location do you want to jump to? You want to jump to address location 0 because that's where this instruction starts, right? Which means your offset should be minus 16. Your offset should be minus 16, right? Because if your offset is 16, again, your offset, if it is minus 16, you jump back to this. So the question here is very simple, right? Because this offset has to be minus 16, the answer also here is minus 16. Very simple question. Okay, slightly lengthy to read, but once you understand how PC relative addressing works, what is the size of each instruction, and if you write this thing down carefully, and if you know that in the program counter you have 16, you have to add the offset to this to reach the final branched or to reach the final destination. It's very simple to compute, right? Again, these problems in computer organization are simple if you have gotten your conceptual understanding of each of these concepts correct. It's a very simple thing otherwise. Just draw diagrams, write numbers, simple mathematics, you can solve it.